It is my great honor to have Chiao Liu to speak to us today. But before I introduce Chiao, let me just acknowledge that this series is a collaboration between Gerg Institute for Data Science and the River Campus Libraries. And this whole series has been supported by the NSF NRT grant. It's an interdisciplinary graduate training grant for augmented virtual reality at the University of Rochester. And this entire session is going to be recorded. Actually, it's going to be recorded and the video will be made available later. So with that, let me introduce you, Dr. Chiao Liu. So he received his PhD in EE from Stanford, and early in his career, he was part of the team that developed the very first CMOS time-of-flight sensors, and then he was later a technical fellow at Fairchild Imaging, worked on a wide range of scientific and medical imaging systems, and later in 2012, he joined Microsoft as a principal architect and was part of the first generation HoloLens AR team. And then currently he is at Facebook Reality Labs and basically running the sensors and systems research there. And so today he's going to talk to us about sensing and computing technologies for AR and VR. So with this, welcome, Chiao, and we're looking forward to your talk.
Yeah, thank you, Yuhao, for the introduction. Now let me share my screen. Right, I hope you can all see now. All right, yeah, let's go ahead and start. So I guess today I want to sort of just give a quick introduction about the sensing and the computing technology that is, developed and used in the AR/VR devices. Yeah, just sort of a quick bio. Again, I got my PhD from Stanford and I've been working in Canasta. That's sort of that period of time I was focusing on the 3D time flight sensor. And then later on, I moved on to Fairchild Imaging, and the work there was focused mostly on scientific and medical imaging applications. And then I moved on to Microsoft, and was lucky enough to be part of the first generation HoloLens AR team. So the HoloLens is sort of the first, all tethered, AR devices. And right now I'm working at Facebook Reality Labs, and my whole team is working on both the sensing and the system, computing kind of research. So the agenda today, I'm thinking that let's sort of start with a quick introduction of some use case of images and the cameras, how they are used for the AR/VR devices. And then I will sort of go a little bit deeper and give a very quick tutorial on CMOS image sensor technology. And then the third part of the talk is a sort of a sensor developed within my team that we demonstrate, the ultra wide dynamic range capability using the so-called digital pixel sensor. And finally, we move on to the system level and looking at, giving, all the power and all the, compute constraints, what would be the optimal overall system architecture look like. So with that, let's go to the first topic. Yeah, so Facebook, embarked on this long-term, development, in the AR/VR domain, and the belief at Facebook is that the AR/VR devices will be the next generation computing platform. Essentially, this is what's going to happen after the cell phone we are using today. And we start this journey 6 years ago by the acquisition of Oculus. And in the early years, there are various sort of developers case, the DK1, DK2. And then the first commercially available product is the Oculus Rift. But Oculus Rift actually is a fully tethered device. At that time, you have to have a high-end PC connected, through a long cable to the HMD, and then the camera also has to be mounted outside, on the wall or on your desk to look into the the user. And then I think about 2-3 years ago, we launched the Oculus Quest. Quest is the first untethered device So, in the HMD or in the head, device, basically you have the compute, you have the display, you have the battery, you have everything, all integrate together. And that also comes with, the remote controller. And then last year, we have another, launch, which is the Quest 2. The Quest 2 compared with Quest have a much better display quality, much, lower power consumption. And there are like, a lot of, nice, games come out together with Quest 2. Early this year, or maybe, very late last year, we also announced the first AR glass called Area. But actually, Area is more like a research vehicle. This is not commercially available to general public. This is more like our first attempt to do a sort of AR type of a glass. It doesn't have the virtual display, but it has all the necessary cameras, as you can see from this picture. And this is, sort of a good device, a good prototype for us to get the, a sort of, the first user experience. The ultimate goal is showing on the upper right corner. This is what we envisioned, a stylish, very compact, very, light-weighted AR glass, where, in addition to, all the functions, you can also have the virtual display there. Right. So again, this is just a zoom-in picture of the Quest. Quest is the first untethered device. As you can see that it has 4 cameras, and has come with the 2 remote controller. The remote controller actually has a built-in LED rings, around the rim, and then the camera was able to tracking, the ring, the LEDs on the remote controller, and that's the way you use to track, the user's hand movement. And the Quest 2 is upgraded device. As I said, the biggest change is a much better, display quality. So what can AR glass do? Essentially, in our vision, the AR can do is basically superimpose a virtual object on a physical, environment, right? Like, for example, here, we can play a virtual chess game, on a physical table, right? And you can see that in order to do that, there's a lot of, underlying computer vision functions and algorithms need to be running in real time. And then, with this AR device, you can further enhance, the user's experience and, empower them by, for example, during a meeting, right? You show the real time, statistical data, right? During some kind of a technical discussion, or you can, translate, assign, automatically, right? From one language to another language, and then when you meet a new person, right? He or her, name will automatically show up so that, can remind you, hey, what the person's name and things like that. So those are sort of some, sample, use cases, we've been, thinking about. And at the sort of, this is a very simple breakdown in terms of what it takes, right, to deliver those kind of, functions. If you look at, essentially, I divided it into 3 layers. At the bottom is all the basic functions that including, sensing and the tracking function, including the optics and the display, and also audio is another element. And then on the second layer is about, the user interface and things like that. I believe one of my colleagues, gave you guys a lecture last week talking about the user interactions. And then at the top level, it's about the overall system design. And then further on top of that, there'll be, all kinds of applications that we can enable, our developers and, other users to develop. So that is sort of a very, very simple breakdown of, the overall, multi-layers of the AR system. And then now, if you look at it just for the sensing and the tracking functions, there's still, a lot of different category of things we have to do. Everything has to be mapped into a physical world, right? This is the physical, 3D world. And then, we have to, first of all, tracking, the user's head orientation and head location. So that is the tracking, the using SLAM, right, to understand where the user is and what's the orientation of when he wears these devices. And further, we have to track both the physical object in the world as well as the user's body part as well, right? That's including hand tracking and eye tracking. The eye tracking itself is another critical thing, because you want to understand even both, I guess, either in the virtual display or in the in the VR device or the AR device, where the user's gazing direction is, and from there actually you can get a lot of interactions and signals. Now, this is sort of a very quick video just to show how the SLAM works. I guess you guys probably already are taking those computer vision class, right? So basically, when you start wearing this device, the first thing the device does actually is to extract the physical features out of your environment. And then, based on those multi-camera view, basically we can estimate the depths of those features, and then build a map, a physical feature map in your surrounding. And with this map, then you can running the tracking functions and using that to interpolate or to derive the user's own position in the physical world. And this tracking and map building is running in parallel, right? And in real time. So that is the first use case for the cameras. The second use case is the hand tracking applications we developed. Here, actually, what I'm showing is that instead of using the remote controller, and based on the tracking the LED, we also developed some algorithm that can just track user's native hand. And in this case, basically, you have to, for each hand, you have to estimate the joint location, and for each hand there are 21 joints. So that is sort of what the algorithm does behind the scene, right? Once you understand the joint location, then you can start modeling the hand movement and enable all the interactions with the device. And the third application is the eye tracking. Again, here the user's eye actually is illuminated by near IR light source, and we have a ring of LEDs, at the back side of the display, and those LED generated the glint, on the eyeball, and then now, by tracking this, glint location, and based on particular eye model, you can sort of expect where the eyeball center, where the gazing direction. And from there, again, you understand the user's intention and things like that. So that's another application. But if you think about the eye movement actually is very rapid, right? So this kind of a camera really needed to be operated at a very high speed, and you have to be able to extract the information also running at a very high speed. So those are the sort of several examples of why we have to have a camera mounted on the AR devices and what are the camera used for. But in summary, if you're looking down into what kind of requirement is needed for those cameras, and sort of list some high level stuff. So the first thing is that for all those computer vision applications, the ideal case is you have a global shutter sensor. Later on, I will go to the detail about the difference between global shutter and the rolling shutter pixel. But as at a high level, basically that if for all the computer vision, or especially for all those tracking functions, a rolling shutter might suffer from the motion distortion, and global shutter is a preferred choice. The second requirement is for all those sensors, right? We need very high low light sensitivity. We need a very high near IR and visible sensitivity. For example, for eye tracking, right? Given that it's using the external LED light source, the higher the sensitivity you have, the lower power required, right? To illuminate. So that's a sort of overall power benefit. For the AR device, a true AR device should be enable the user to use day and night, indoor and outdoor. Now, when you walk around in this kind of a totally uncontrollable, lighting condition environment, the dynamic range of the sensor is critical. So, a wide dynamic range is definitely preferred choice. And also, I mentioned before, right, for some of the applications, eye tracking, for example, you do need, operate at a very high frame rate. Today, maybe we can operate at 90 frames per second, but the higher, let's say, if we can go to 120 or 240, that'll be even better. And as you can understand, given that this is supposed to be a compact, low weight, yes, fashionable device, the power consumption is critical because you simply cannot put a big battery on your glass, right? So in terms of power consumption, in terms of form factor, in terms of weight, those are all critical aspects of a viable consumer device. So next, let me go a little bit deeper and give a very quick tutorial on some CMOS image sensor based. So we start from looking at the light property, right? So what I'm listing here really is like, for different color of light, what the kind of wavelengths, where they're corresponding to. And also remember, the photon energy listed in the parentheses, those are the energies that, we will be used, right, to detect those photons. And then, another way of looking at, the environment basically is what is the, the photon flux or what's the illumination level, and typically using lux. And as shown on the right side, if you are looking at, the bright sunlight versus the moonless light, actually we are looking at an order of magnitude kind of difference, right? Now, again, as I mentioned, for AR device, you do have to enable the user to use day, night, indoor, outdoor. So, you can easily, the camera on the AR glass can easily face in the situation where you can have a 6 order magnitude of, of light intensity different, even within a single field of view. Right, so for 6 order magnitude, what effectively required is the 120 dB of dynamic range. So that is sort of the kind of the environment those camera sensors need to be operated at. Now, how do we generate an image? Right, we start first again by absorbing those photons. And the absorption material actually is the silicon, which is the most common and most well understood material, right? The good thing about silicon is that its band energy band is only 1.12 electron volts, right? And if you remember, the photon energy we listed here, then actually each photon do have a higher energy than the energy band, and as such that each photons can generate electron hole pairs. So this is actually quite lucky because if because of this, now we can take advantage of this gigantic semiconductor industry, right? All the sophisticated technologies, right, for us to use to build the sensor. Now imagine if it has to be a different material, right? Then your camera will not be like $10, as cheap as we have today. The next thing is about the absorption, right? So at the right bottom, I'm showing the silicon absorption as a function of wavelengths and as a function of the silicon thickness. If you just focus on, let's say the silicon thickness is 3 micron, then at a 3 micron of a piece of a silicon, right? The light, up to 500 nanometer, for example, can be fully absorbed. Meanwhile, for the near infrared at 800 nanometer, for example, right, you probably only be able to absorb the 30-40% of the light, right? So this is another property of the silicon of a light absorption. The next step is that how do we effectively eventually generate a digital picture, right? So first of all, we start by using silicon to convert the photons into electron hole pairs, and then once those free charges generated, we have this photodiode, and especially, the depletion region in the photodiode, that is where, the photon electrons are accumulated or integrated, right? So now within the certain, exposure time, let's say we accumulate a certain number of photon electrons, that is our charge signal. The next step is that we want to convert this charge signal into a voltage signal. Now, I guess, the basic EE is that, if you dump this amount of charge into a fixed capacitor, right, then you can detect, the kind of a voltage you get out from, the capacitor. Now we can have a two-way of, get this conversion. One is just using the parasitic, the built-in capacitor of the photodiode itself, or we can, do a charge transfer. If we have another capacitor, we move this amount of charge from the photodiode onto that capacitor. Both ways we can convert the electrons into, the voltage signal. This conversion is the so-called conversion gain, right? It's the inverse function of the capacitance. So if you have a small capacitor, then, giving the fixed amount of charge, you can have a much higher voltage signal. If you have a larger capacitor, your voltage signal will be lower. Now, with the higher voltage, basically, now you can have a stronger signal, right? As such that, if you think about the readout chain, the downstream noise can be effectively reduced. But on the other hand, with the larger voltage swing, you could easily saturate the downstream, voltage, right? So there is a balance between, how much of a, conversion gain or how much of capacitance I want to use on the front end to achieve either, low noise or, high, voltage swing or high signal range. So that's the second step of converting from charge into voltage domain. The third step is, how to digitize it, right? Typically you're using ADC, and then, in a real, practical implementation on the sensor, you could have a different architecture. For example, you could have a single ADC per sensor, or you could have a single ADC per column, or you can have a, single ADC per pixel. So, now let me focus a little bit more on a very, this is sort of the dominant pixel type today, right? This is the so-called 4 transistor rolling shutter pixel. Here, the reason it called 4 transistor, basically you have the transfer gate, you have the reset gate, you have the source follower, and then you have the row selection. And then the photodiode consists of this so-called N- layer sandwiched by the P plus and the P silicon, right? So this N- layer is fully depleted, and that is where the charge is stored during the exposure. The transfer gate, you can think of this as a switch. So when the transfer gate is turning high, the charge inside the N- will move to the right to the N+. And the N+ has, the built-in capacitor, right? So that is where, the charge is converted into a voltage signal. And afterward, the source follower basically serves as a buffer. And then, the voltage signal will show up on the column bus when the row is selected. And that is, where you start, read out the signal from the pixel, right? So that is the sort of, the working mechanism of the rolling shutter pixel. Another way of looking at this is looking at the so-called potential diagram, where basically you can think of the charge as, you are collecting charge as you are collecting water, right? So the water tend to move to the, to the lower altitude. So in this case, basically that we have a bucket, on the left side, this is the N- to accumulate the charge. And then we have another bucket on the right side. This is the N+ of the floating diffusion node. And in between is the transfer gate, right? To decide, whether you want to move the charge, if you want to transfer the charge or not. And there's another thing here, typically you hear a lot is so-called correlated double sampling, or CDS. Effectively, what it does is that, is to read out the signal twice. The first time you read this, you read, the amount of a charge, right after you reset the floating diffusion. This is before you do the charge transfer, right? So that is set your reference level. And then afterward, you turn on the transfer gate and you do the charge transfer. And then you are at a different, wattage level or water level, right? Now, with this reference level and the new level, and you do the subtraction, that will be, the delta will be your real signal. And that is where, you get your signal. And in the next slides, I will show why you want to do that. It's simply because, during the operation of the pixel, actually there are multiple noise sources, right? There's the KTC noise, which happening whenever you have a resistive path to reset a capacitor, right? That's the KTC noise. And you also have the thermal and the 11F noise that are associated with any, transistors. And then you also have the fixed pattern noise that effectively, represent, the VT mismatch, the transistor size mismatch, and all the, non-ideal situation in a CMOS fabrication process, right? The fixed pattern noise, based on the name, is sort of a fixed. You can think of as a fixed offset. So as shown in the time diagram, on the left side, if I do two samples, right, on the bit line, the first sample is I sample the voltage level right after the reset. And the second sample, sample 2, is I sample right after, the charge transfer. And I do subtraction between the two. Effectively, as you can see that this subtraction help you cancel both the fixed pattern noise as well as the KTC noise. And what left is the real signal itself, right? So the CTS actually is a very effective way of reducing all the noise sources and give you a high quality signal. So with that pixel described, now we can start building a sensor, right? What it essentially does is basically that we put this array of pixels together. We connected horizontally using the word line and connected them vertically using the bit line, right? And then during the readout, basically we using the vertical scan circuit to select one row at a time. We turn the selection transistor on, and so that the pixel can be connected to the vertical bit line, right? And then we do the correlated double sampling, and then the voltage will show up at the bottom of the bit line. Now from here you could either put a ADC at the bottom of each column, or you could have a single ADC, and then you just multiplex those voltage signal at various columns right into this single ADC. So at the nutshell, this is how image sensor structured. You probably, again, I mentioned at the beginning, right, for computer vision, actually the preferred choice is a global shutter. The reason it's called global shutter really is that, we want all the pixels start exposure at the same time, and we want all the pixels to end the exposure at the same time. For the rolling shutter, you cannot do that. In the rolling shutter, you have to start and end the exposure for each row at the time, and their exposure time are sort of staggered, right? So that is the sort of, you have the rolling exposure window. For the global shutter, what you prefer is everything operates simultaneously, right? Every pixel operates simultaneously. Now, in order to do that, we have to modify the rolling shutter pixel by adding 2 more transistors and 1 storage node. So as shown here, the additional transistor 1 is this so-called shutter gate on the left, and then this another transfer gate 2 on the right. And then the pinned SD or storage node, as this is another storage photodiode. So what is showing here basically that first of all, the transfer gate 1 is off, but the shutter gate is on, right? So the photodiode cannot store any charge. Then the moment we turn off the shutter gate, the exposure started. The charge accumulated inside the pinned photodiode. And then at the end of the exposure, everybody turned on the transfer gate 1 at the same time. So the charge now moves from the pinned photodiode onto the storage node, right? And the storage node is protected, meaning that we will put a light shield there. So once the charges move into the storage node, it will not, accumulate further. And then from there on, it's kind of like the rolling shutter operation, right? Then we started doing a reset on the FD node, and then we sample it. Then we do the charge transfer by turn the transfer gate 2, right? And we move the charge from the storage node onto the FD, and then we do the sample again, and then we do the subtraction. So this is sort of how a global shutter pixel works. As you can see that it's nice in terms of with this mechanism we can control the exposure simultaneous for all the pixel. But on the other hand, now you have a more transistors per pixel, and so the in general the global shutter pixel is have a larger pixel size than the rolling shutter pixel. And finally, there's also another type of device we could use, pixel we could build. We call this digital pixel. By the name, basically that we want to do the quantization inside each pixel, right? So what we're going to do that we put an ADC and also a digital memory inside each pixel. Now, as such that, the output from this pixel now is just, pure digital bits, right? There's no voltage signal needed to be read out, and they need to be carefully, conditioned. So that's a sort of a new type of digital pixel. And the next section, actually, I will describe one of the implementation, we did back at Facebook Reality Labs. Before I talk about the detailed pixel circuit, let me also introduce the fabrication process for a digital pixel sensor. Here, the advanced of a CMOS fabrication process these days allow us to use the so-called stacking process. What does that mean? That you have a 2-layer of silicon, right? You fabricate each layer of a silicon separately, and then you are, flip the first layer of silicon and make it face to face, and connect it to the second layer of silicon. And the connection is done by the so-called hybrid bump, which is showing the dark rectangle in the picture, right? This hybrid bump can be as small and as tight enough that you can have a multiple those kind of bump connections at the pixel level. Right, and then this builds the electrical connection from the first layer of silicon to the second layer of silicon. And in this picture, what I'm showing here, that after you've done this bonding, you further grind down the backside of the first layer of silicon. You only leave, about a few micron thickness of silicon, and then on top of that, you deposit the color filter and the micro lens, right? And with that, basically, what it does is that it allows you to use the first silicon optimized just for the sensing application. And then your part of the pixel circuit can be put on the second layer silicon, in this particular example, the ADC, right? As such that, now you can have this vertically stacked, structure, right? And as such that you don't have to, have a gigantic pixel. Right, and look another way that all the ADC circuit now is hiding beneath the photodiode. So this is sort of for the sensor guys, this is kind of like the best of the both world, right? Now also you can decouple the process node of the CIS layer from the ADC layer and optimize each layer accordingly. So with that process, we build this computer vision optimized sensor. DPS, right? We have 2 layers. The first layer 45 nanometer process node, second layer 65, and again, like I said, the first layer is really optimized for the light detection, to have the best QE, best dark current, things like that. And then the second layer is really optimized for power consumption, right? And as you see that at 30 frames per second, actually the total power consumption is only 5 milliwatts. And also given that this is a digital pixel, we can operate the sensor very fast. We can go up to 480 frames per second. Actually, even at 480 frames per second, the dominant factor actually is the I/O bandwidth, not necessarily the pixel operation speed. And with that, now we can sort of, looking a little bit of detail about how the pixel circuit is designed. If you look at this circuit, it's actually very similar to the 40 pixel or maybe the global shutter pixel, except that now we have a two capacitor, right? We have this parasitic FD capacitance, and then we also have this CS capacitor. And the two can be connected together by turning on the DCG gate, right? So with this kind of mechanism now for the pixel, we can have a two gain operation, right? If we disconnect this DCG gate, we only convert the charge on the FD node. And if we keep the FD capacitance small enough, we're going to have a very high gain operation. And if we turn on the DCG gate and connect a much larger CS capacitor to the FD, we will have a larger capacitance, and then we will have a low conversion gain. But on the hand, this low conversion gain will allow this capacitor or this combined capacitor to hold more charge, right? So that gave us much wider dynamic range capability, right? And from there, the signal, the voltage signal is again buffered by the source follower transistor, and then using the metal connection, connect this voltage signal onto the second layer to quantize. And what's showing here is the pixel on the second layer, where we have a very simple ADC type called single slope ADC, right? And then what it takes is just have this comparator circuit as well as the 10 bits of a digital memory. Each memory cell is a 6 transistor SRAM cell, right? So the single slope ADC basically works is that you have a fixed input analog voltage on one input of the capacitor, and then you apply a linear ramp on the ramp signal, right? Whenever the two voltage cross with each other, the comparator will flip, and then the comparator flip will latch the memory. Before the memory latched, you have the global digital count, feed into all the memory cells. The moment you latch that digital count, that represents, your real signal level, right, inside each pixel. And this can operate at a very fast, each ADC operation only takes 20 microseconds. With this, now we can introduce the so-called triple quantization scheme. Again, I sort of already talked about the low gain mode and the high gain mode. And with the pixel level ADC, we can introduce a third mode operation. We call this TTS, or time to saturation. Effectively, what this does is that now think of this ADC instead of analog to digital quantizer, it now becomes a time counter. What it does is that we're using this ADC to monitor the voltage level on the capacitor, right? If the pixel is under very bright level and bright light level, then this voltage signal will reach a ceiling, right? Reach a threshold very quickly, even before the end of exposure. But if the ADC is a time counter, when it reaches the ceiling, I already be able to count the amount of time it takes to reach that level, right? Again, all of this is before the end of the exposure. And then my digital count during this time, again, is a representation of the light level. But now you have this kind of inverse relationship, right? The stronger the light, the less time it takes to saturate, right? And my, the smaller digital count I will latch in my memory, right? Now with this third mode operation, effectively we can use the pixel to detect a very bright light, right? So that really gives us the capability of have a very wide dynamic range using this kind of a digital pixel. And what I'm showing here is the relationship between the input light versus the output digital bits. And again, here we have a 10 bits memory, right? So the maximum digital count we can have is 1024, right? And then further we break this into 3 regions of operation. We have the PDADC, which is a high gain mode that is focused on the very low light region. We have the middle region, FDADC, that's the low gain mode. And then for any light beyond that FDADC will go into the TTS mode, where we can further extend, right? So now if you look at the x-axis, right, between 10 to the power 4 lux versus 0.01 lux, that effect is 6th order magnitude or 120 dB, right? The measured result shows that the sensor can operate at 127 dB. And visually to show the dynamic range is showing here. So the test chart is a 20 patch chart. By changing the neutral density of each individual patch, effectively, those patch can cover, again, 6th order magnitude kind of light intensity level. We shine the light from the backside of this chart, and then we capture the picture from the front side. But in order for us to show, to display, we can capture this 120 dB. We need to break the single capture image into 2 display, so that we can look at the gray level difference on the lower end as well as the gray level difference on the high end. But the point here is that if you can see the green level difference, that basically means that we can capture, this total 120 dB dynamic range within a single exposure, within a single image capture, right? So that is sort of a demonstration of the high dynamic range capability.
Hey, Chiao, I had a question. Could I ask? Yeah, I was wondering, so the TTS is incredibly clever. I was wondering, so you basically use the ATC as a timer to count, and then you can scale with the actual exposure time to roughly estimate what the flux would be if your pixel size is much bigger, right? Yes. So I think that's very clever. I was wondering if this is an invention in this paper, or people have kind of tried similar things before.
There were similar idea before. The real invention here is how you can combine this TTS with the other 2 mode, right? Because if you just operate the pixel in the TTS mode, actually you can only detect the bright light, right? For the low light, you are not going to get good result. Remember, our goal is not just for the capture the highlight, but the sensor should also have a very good low light performance as well.
I see. Yeah, and then that gets to the second question, which is you have the other 2 modes, and then it seems like in the low light the gain is higher and the mid light the gain is lower. So is it basically suggesting that? So I haven't done the calculation, but is it suggesting that for the mid light range, you quantize more, so you lose accuracy more there? Because
your step size is wider, right?
Step size is wider. So
right.
So then you are essentially, so the accuracy there, the flux accuracy there is a little bit lower than the mid light, than the low light where the step size is narrower. So is it driven by some characterization at the application level that the accuracy, the flux at the mid light level is not that important compared to the 2 extremes? Yeah.
Actually, that's a very good point. I mean, effectively, what you talk about is signal to noise ratio, right? So from the algorithm point of view, as long as SNR is about a certain level, for example, 20 dB, right? Then it's good enough. You don't have to, have a very high SNR. So yes, at the PDADC, you have a lower noise. In the FDADC, now your noise level is higher, but still, actually, your SNR is increasing because the noise is dominated by short noise, right? The short noise, the variance is a standard deviation is the square root of the signal. So as the light getting stronger, actually your SNR actually is still increasing.
Yeah, I see. So at low light, because the SNR is lower, so you need kind of a higher accuracy to.
Yeah. You have to pay attention to the noise more carefully in the low light region.
Okay. Yeah. Thanks.
Yeah. All right. Yeah, so this is another example of a high dynamic range image, right? What we are looking at here is a turned on light bulb with other object, and the first picture I'm showing here, this is only if the sensor is only operating in the TTS mode. As you can see that we can see the light bulb, and we can even see some part of the filament inside the light bulb, right? As well as a ladder on the bulb itself. And then, getting to the middle region or the FTADC range, now we see more object, right? We see the shield of the light bulb and even, some features behind that. But some region of this light bulb now is saturated, right? And then in the third picture, when the sensor is operating in the high gain mode, the PDADC mode, we see more details underneath the light bulb or behind the light bulb. There's a water bottle there. But now you can see that the whole bulb region, right, the whole light region is completely saturated, right? This just to show that, within different mode operation, you do have a different way, sort of different capability of handle different light region. And now if we put everything together, actually just, sort of run this 3 mode sequentially and combining the final image together, this is what we can see, right? So with this now you can see both the very bright filament as well as the, the water bottle behind that. So again, this is sort of a real thing demonstration of the high dynamic range capability.
So I was wondering what you think, whether it's reasonable to push a sensor like this to kind of a smartphone camera, like consumer cameras for photography. I was wondering if the economy is not going to work out because it's just too costly to manufacture something like this. So in low-end consumer cameras, maybe using computational photography algorithms make more sense for HDR. Yeah, it's for different market. I guess the pixel here is still bigger, right, than the 1 micron pixel in the cell phone, and simply you cannot build a multi-meg pixel DPI sensor, right? That will be a very a very gigantic, very big. And also I guess in the cell phone people optimize for photographic quality. Here what we really care is just how we can use this kind of sensor to extract the right amount of information, right, for the algorithm to consume rather than human eyeball. Yeah, thanks.
Yep. All right, let me get to the last topic of today's discussion. Again, this is sort of let's jump out from the sensor now and looking at the overall system architecture level. The first thing we want to understand really is that, for the AR glass to be operate in real time, always on, right, and enable all those functions, what are the compute costs, right? And here, what is showing here is the normalized energy as different operation, right? As a unit, we use the just the integer 8-bit adder as a base energy unit, and then look at other functions. For example, if we do 16-bit integer mag operation, right? How much energy that will cost with reference to 8-bit adder, and then how much of SRAM write operation cost us, right? 1 byte of SRAM or floating point operation, how much that costs. And then move to the right, you see that it's getting more and more expensive, right? A NOC, which is the network on chip, right? That is just transmit a 1 byte of information from one part of the chip to another part of the chip. Actually take lots 480x of energy, and then do an 8-bit adder. Right, and then finally, if you look at the wireless communicate or transmit a byte through wireless link, how much more expensive that is compared with again a 8-bit adder, right? So as you can see that in general, right, the data transfer, data storage is a lot more expensive than the simple digital compute itself, right? And looking another way is that, I talk about the SLAM application and the hand tracking application. And this is, the power breakdown, right? To enable those applications, right? For example, looking at the SLAM, right? The compute actually only costs us, less than, 1/5 of the total power, right? The rest actually is burned mostly by the memories and by the, the data communication. And it's a similar thing, for the hand tracking as well, right? So what this does really is that, okay, now we have the camera, we have a lot, multiple sensors, right? And we have the algorithm requires a particular latency, because you want to have a real-time interaction, right? We have to ship all the data from the camera onto a SoC to do the compute, and then all those, different application actually, have a different flavor of algorithm and things like that. So globally, how do we optimize this system, right? How do we, partition, the sensing and the compute? And the sort of a, very high level conclusion is that, we better do this in a distributed sensing and a compute architecture rather than, a centralized architecture where, all the sensors just simply collect the raw data and shift into a, high performance SoC to do the job, in a single, centralized kind of a configuration. So this is sort of another way, of looking at how can we, do this a little bit smarter in terms of, let's say, we have 3 layers of compute, right? The first layer is directly on the sensor node. So in addition to the CMOS image sensor, we might have some processing integrate directly inside the sensor. And then the second layer is the aggregator or the main SoC on the glass, right? And the connection between the first and second layer typically is copper wire, kind of a bus, right? And in this case, typically using MIPI, protocol. And then the third layer of compute actually done in the cloud, right? But in order to shift the data from the second layer to third layer, you have to use a wireless link. So that's kind of a breakdown of different level of compute, and then we can specify, what are the sort of the data communication costs, on the MIPI versus on the wireless, and then what kind of processing we want to do at the sensor layer on the glass and in the cloud. Right. So and we build a very simple model. By no means this is exhaustive and to the very precise level. But this already can tell us a little bit of all the trade-off we have to think about. Right. So first of all, we have to understand at what process node we can use, right, for the compute on the sensor, and for the compute in the main SoC. I mean, the main SoC typically, you talk about, let's say, the Snapdragon from Qualcomm, right? I mean, they always using the most advanced node, 7 nanometer today, or maybe already moved to 5 nanometer, right? But, on the sensor, typically you have, 1 or 2 generation behind, right? So here, at least the 3 scenario, the sensors, for example, can have a 7 nanometer process or 16 or 14 nanometer process. Then there's another consideration is that effectively how many operations you want to do per pixel of raw data, right? Is that like a 10 operation per pixel, or 100 operation per pixel, or 10,000 operation per pixel, right? Again, this depends on algorithm, depends on the application. Some of the neural network do get to 10,000 operation per pixel kind of a range, right? So we break this down into 3 kind of panels, and then from there you can also sort of have this sliding bar, like in terms of how much of percentage of compute I want to do it on the sensor versus on the aggregator, right, versus in the cloud. And with this sliding bar, now you can basically distribute this energy in different way. Okay, all the variables are the processing node, right? The kind of algorithm needed to be performed, and how you partition those algorithms at the different layers, and from there we can get a different sort of a optimization point. So without going into detail, I guess just at a high level, this is sort of how you start using this simple model, right? Try to understand all the trade-off and all the knobs you can play. All right. So with that, effectively now, I hope you get a little bit better picture in terms of what we are doing here at the Facebook Reality Lab, and now looking at the technology behind this, right? Really, there's sort of a 3 legs, or actually maybe even more than 3, right? We have to look at as technology advances, what kind of memory that give us the best performance that lowers the energy cost. Right, that's my, including, sort of non-volatile memory, right, for example. And then we also, horizontally look at, what are the latest cutting edge process node, 765, or, the GAA, right, all those kind of latest, CMOS technology. And finally, also, in terms of sensor particular, right, what kind of continue improve in terms of sensor performance, in terms of a stacking process, and even optics design and things like that. So that's kind of like just on the technology side, all the directions we have to pursue simultaneously. So anyway, as I said in the beginning, right, the journey to AR, to the ultimate AR device, actually going to be very long. It's going to be a very exciting journey, and there are still a lot of technology challenges needed to be overcome. And I'm glad we are on this journey, and I hope you also found that this is exciting, and this is something you want to dedicate your career into this as well. With that, thank you very much. Happy to answer any questions.
Yeah, thank you, Chiao. I think we still have a little bit time left. So any questions from the audience, students, and others?
So I have a question. In your power breakdown slide, so there's like 3% interconnect power, and most of it is the like memory power. What's included in that interconnect power consumption?
Yeah, that basically is the connection between the sensor to the SoC, right? Again, like I said, this is typically using MIPI, right? So transmit a bits, right, from the sensor onto the SoC is about 3 to 4 picojoule per bits kind of energy.
Okay, and in the memory power consumption portion, which is the largest portion, so there is also interconnect related power loss as well, right?
Yeah, that's again, if you have to store multiple frame, and if those frame has to go to the DRAM, right, in and out of the DRAM, that's actually very high cost. So that is a part of reason why the memory, SRAM plus DRAM takes 78% of total energy.
Okay, so in this memory power, like 78%, how much of it is related to only memory and like communication related to memory? Can you make a division among them?
Yeah, actually, yeah, sorry. When we say like a DRAM, right, again, this is including communication, right? Because, DRAM actually is off chip, right? You cannot, have a DRAM integrate directly on the SoC. And then, you go through all those DMAs and stuff. So that's where, it's getting very costly, very expensive.
Thank you.
Yeah, any questions from the audience? I know we have a lot of people here.
So with all the advancements being made with the cameras and the sensors, are there any adaptations you have to do to the computer vision algorithms?
Yes, it's a very open field. I mean, I think there are a lot of opportunity for innovation, and there's a lot of opportunity for the so-called co-optimization, right? You are optimizing the sensing modality and the compute, simultaneously, right? So I think that is, the best way of, get to the optimal solution, right? Is, looking at what you can take the advantage of on the hardware side, as well as with the particular, characteristics of the hardware. How can you, modify your algorithm, accordingly?
I mean, specifically with like the data though, because presumably a lot of the data was taken without these advancements.
Right. Yeah. I can give you one example. Is you probably heard about the so-called event sensor, right? In that case, basically that, they are using, event-driven pixel output, right? You're only reporting, the change of the thing, when you only sort of report your information, shift your information to the processor when particular pixel detect the event change, right? That way you can reduce the amount of redundancy.
I was wondering if you can give a rough estimation of the power envelope here, like what is the total power constraint that you're working with, and how is the cooling system going to work? It seems like cooling is going to be incredibly difficult.
It is actually, that's the ultimate from AR glass form factor, right? I mean, if you think about, our glass frame kind of thing, right? The thermal dissipation is the limiting factor. And, just simply based on the total amount of surface area you can get of this device, you can easily derive that, it has to be, I don't know, 500 milliwatt to 700 milliwatt range.
Okay, I was just taking notes of that number because I had never heard of specific numbers about the power envelope, which I think is, incredibly tight. I mean, so it's not, and I think it's limited both by thermal because it's literally touching the skin, as well as the energy budget, because I cannot imagine you can pack like a huge battery into this thing.
Yeah, you can, but even if you want to run the device full throttle, right? Just quickly you will overheat, and quickly you have to throttle back, right?
So any kind of interesting cooling technologies that are being invented there?
Well, it has to be passive cooling, right? You can't put a fan.
Yeah.
Right. So yeah, we do have experts there, just to look at that, right? It's about the material, it's about, sort of overall thermal design. Yeah. Okay. And by the way, this 700 milliwatt, right, including the display itself, right? It's not just for sensor, not just for compute. Actually, if you break that down, the display costs a lot more than the sensor itself.
Yeah, I see. So that's actually, so we did a bit of study before on smartphones where the display, when it's active, consumes higher power than the SoC itself, which I assume the gap is going to be more or less exaggerated here. So I was wondering if you can comment a bit about the actual kind of percentage-wise, how much power or energy?
I can't. Sorry. I mean, it's really depends on sort of the whole display technology, right? Because that is effectively, you can think of that reverse path, right? You have to generate photons, right, using whatever LED or laser, right? And then you have to propagate those photons through kind of a waveguide, right? And eventually project this onto user's eye. And the overall path, actually, in terms of efficiency, is quite low. It's probably like, out of million photons you generated, I don't know, tens or hundred, photons eventually reach the user's eye.
I see.
Right.
Yeah. Thanks. Any other questions from the audience, from the students, actually?
On the slide when you break up, anyone else? Sorry. So on the slide when you break down the power consumption as a function of the in fact like 3 slides later, when we break down the power consumption as a function of this one as a function of the operating power and the manufacturing. I know it's a qualitative analyze, but at the technology of like 2021, what would be an ideal choice of the combination here? Say if we are building a AR glass at this time, given our current technology, what would be your choice on this coordinates?
Well, it's obvious, right? Again, if we can have the most advanced node on the sensor, that's a sort of ideal case, right? Because now you do all the compute directly on the sensor. You don't have to ship, megabyte of information, right? So, especially like, for example, for the eye tracking example, right? At the end of the day, right, what you need is just the gazing vector, right? So if you can finish all those directly on the sensor, then you save all the energy required to do the raw picture transform. Okay. but there are practical consideration, right? Today no fab can help you do a 7-nanometer sensor because you have other considerations. You have to optimize the imaging performance as well.
Yeah. Okay.
Excuse me, I have a question. I tried to download your article, like intelligent version system, but it's very challenging. Like all the website need to pay. I mean, is it free for public now?
Sorry, I didn't catch your question.
Oh, I tapped in the chat box. I mean, I want to upload. I want to download your article.
The papers.
Yeah,
the
paper.
papers.
I thought I forwarded that to Catherine.
Okay. Thank you.
Yeah. Well, I mean, again, let me know. I guess I can just email you directly if needed.
Oh, thank you. So can I leave my email?
Yeah, please do.
Thank you so much.
Yeah, that would be great. Any other questions for Charlie? I think we have a little bit of time, but obviously we
Yes,
have
so
time.
I had one question.
Yeah.
So in the pie chart, which gave the breakdown of energy consumption, energy consumed in memory operations is quite high. What exact solutions are you looking at to reduce that particular percentage?
Yeah. Again, this all depends on technology. The some emerging memory technology in terms of non-volatile memory, right? Like the STT MEM and things like that, that have a lot of promise. But still, my understanding is that those kind of memory have a very appealing in terms of zero leakage current, right? But on the hand, the write and the read speed are much slower than DRAM or SRAM, right? Or sorry, mostly SRAM, right? So again, you have to balance between the latency associated with those kind of memory, and also I guess there are new field like nowadays a lot of people are talking about the computing memory, right? If you can do the especially implement neural network directly inside the memory, then you don't have to ship the information back and forth, and that's again sounds very promising direction, but my understanding that is still in the very early stage of computing memory, or memory and compute kind of development. There's still a lot of practical technical issues has to be resolved.
Okay. So I have a follow-up question on that. So I have read a couple of papers where people are using certain properties of these emerging memory technologies to build, let's say, accelerators for spiking neural networks. So are there certain properties of these memory technologies that we can leverage to build actual accelerators for image processing or computer vision applications as well?
Sorry, I'm not sure. Is this a question or this a statement?
So the question is, are there certain properties of certain memory technologies that we can use to intelligently build accelerators for computer vision applications?
Yeah, I see. Well, I mean, first of all, again, I'm not the expert there. My understanding that there are two aspects of this is very potentially advantageous, right? Again, one is that you are doing the compute directly inside or near the memory, right? So you don't have to pay the communication cost. And the second thing again is those emerging memory. At least they have a very low leakage or zero leakage, right? It's non-volatile. So especially like when you want to store, a neural network, all the weight parameters there, right? You don't have to sort of, worry about, running, sort of the retention mode all the time and, burning unnecessary power.
Okay.
So, okay, any other questions from the audience? Okay, well, so with this, well, I thought that was incredibly informative. I know I learned a lot, and I'm sure that applies to other people as well. So if there are no other questions, I guess we can thank Chiao again, and I'm sure he's available via email if you have other questions.
Yeah, thank you very much. It was a great time.
Thank you. I
thank you
enjoyed
very
this. Yeah, feel free to reach out to me.
Yeah, thank you. Bye, everybody. Bye, Chiao.
Bye-bye.
Yeah, thank you. Bye bye.